All right, get ready, because this time on our deep dive, we're going really, really small, like way smaller than an atom, small. We're talking about the Large Hadron Collider, the LHC, and all those crazy particle collisions they create.
Yeah, and we're not just talking about smashing things together and seeing what happens. Well, we are, but there's a method to the madness. We're trying to understand these things called boosted objects and how physicists use something called jet substructure to make sense of it all. It's like a giant jigsaw puzzle, but the pieces are subatomic particles.
And from what I can tell from this giant stack of research you gave me on boosted objects and jet substructure of the LHC, it's no walk in the park, right? It sounds seriously complex.
It is. Imagine a particle, like, say, a Higgs boson. You've heard of that one, right? It gets created in one of these high-energy collisions in the LHC, but it decays almost instantly. And I mean instantly.
So how do you even study something that lasts for like a fraction of a second?
That's the challenge. These particles, these boosted objects, they decay into showers of other particles. We call these showers jets. And at the LHC, where everything's moving at close to the speed of light, these jets become a tangled mess.
A mess. I thought physicists liked things, neat and organized.
We do, but imagine trying to figure out what kind of fireworks exploded just by looking at the scattered sparks on the ground. That's kind of what we're dealing with here.
So wait, hold on. Let's back up a sec. How does this whole LHC thing even work? You're smashing protons together, right?
Exactly. Picture this. You have this huge 27-kilometer ring where protons are zipping around, going faster and faster until they reach almost the speed of light. Then, boom, we smash them head on.
Like a demolition derby, but with protons.
And the energy released in those collisions, it's mind-blowing. This is where Einstein's famous equation E=cc comes in. That energy turns into a shower of new particles. Some of them are heavier and more exotic than anything we've ever observed before.
And those are our boosted objects.
Bingo! These particles, like top quarks, W bosons, and yes, even the Higgs boson, they're born with so much energy that they decay practically instantly. And that's how we get those messy particle jets we were talking about.
Okay, so let me see if I've got this straight. We have these particles decaying into these jumbled up jets, and we're trying to figure out what those particles were before they decayed. That's where jet substructure comes in. Like, we're looking at how the particles in the jet are arranged, not just at the individual particles themselves.
You got it. It's
Okay.
like trying to find clues within the chaos. And there are a lot of very clever techniques that physicists are using to do just that. It's pretty amazing stuff.
Okay, you've definitely piqued my curiosity. What are some of these techniques? How are they actually decoding these particle jets? Spill the tea. So we're talking about decoding these particle jets, trying to figure out the secrets hidden inside. One thing I kept seeing in this research was something called Monte Carlo simulations. Now, that sounds a lot more like gambling in Vegas than particle physics.
Well, there's definitely an element of chance involved, but these simulations are crucial for understanding what's happening at the LHC. Imagine trying to recreate a hurricane in a computer, but instead of wind and rain, you're dealing with subatomic particles. It's complicated.
So you're basically running virtual experiments, testing out theories before you even turn on the LHC.
Pretty much. We use all the physics we know, all the equations and models, and we feed that into a supercomputer. Then we hit go and let it simulate millions of particle collisions. It's like a crystal ball, but for particle physics.
So you're getting a sneak peek at what might happen in a real collision.
Exactly. But here's the thing. The simulations don't always agree with each other, especially when it comes to these boosted objects and their jets.
Oh, what kind of disagreements are we talking about?
Well, for example, the simulations might predict different masses for the same type of jet. And I'm not talking about small differences either. Sometimes it's like 20% or more, even after they try to clean up the data.
Wow, 20%. That's a huge difference. Why is that? Do we just not understand these simulations well enough?
It's possible. We're dealing with some of the most complex physics in the universe here. Simulating the strong force, which is what holds quarks and gluons together, is incredibly difficult. And these simulations rely on approximations, which can lead to discrepancies.
So what are physicists doing about this? Are these simulations even useful if they're not perfect?
They're still incredibly valuable. Every time we find a discrepancy, it points to something we need to understand better. Maybe our model of the strong force needs tweaking, or maybe we need to develop entirely new simulation techniques.
So it's a constant back and forth. Experiments at the LHC inform the simulations, and the simulations help us make sense of the experiments.
Exactly. It's a continuous process of refinement. But the really exciting thing is these discrepancies, these little mysteries in the simulations, they might be hinting at something much better.
Yeah, you've got my attention. What could it be? So these discrepancies, these little mysteries hiding in the simulations, they could actually point us towards something revolutionary. I'm on the edge of my seat here.
Well, some physicists believe they might point to some fundamental limitations in how we currently understand the strong force. You see, there are two main theoretical approaches to describing how quarks and gluons behave, especially at those insane LHC energies. We have perturbative QCD, and then there's soft collinear effective theory, or SCE for short.
Two theories battling it out for the top spot. So who's winning? Is it like Coke versus Pepsi in the world of theoretical physics?
I like that analogy. And in this showdown, the LHC is the ultimate judge. But in all seriousness, both theories have their strengths and weaknesses.
All right, break it down for me. What are we talking about here?
Okay, so imagine you're trying to describe a hurricane. You could use all these incredibly detailed meteorological models, track every gust of wind, every change in pressure, or you could take a step back and describe the hurricane's overall shape, its movement, its intensity. Both approaches tell you something valuable, right?
So perturbative QCD is like the super detailed up-close view, and SET is more like the bigger picture, the overall pattern.
That's a great way to put it. Perturbative QCD tries to account for every single interaction between quarks and gluons, but the math gets incredibly messy, incredibly fast, especially when we're talking about non-global logarithms.
Non-global logarithms. Okay, now you're just using big words to sound smart.
It's not my fault they gave them such a complicated name, but basically these non-global logarithms are mathematical terms that pop up in the calculations. And they make it surprisingly difficult to make accurate predictions, especially when we're trying to understand those messy particle jets.
So perturbative QCD has a bit of a math problem, but what about SET? Does it handle these non-global logarithms any better?
That's the interesting thing. SCT, with its more elegant approach, seems to handle those pesky logarithms more gracefully. But it still has its limitations. It's not perfect either.
So it's like each theory has its blind spots. But here's the real kicker you're saying, that by studying these particle jets, these messy clues from boosted objects, we could actually figure out which theory is closer to the truth.
Exactly. It's like the universe is giving us this incredible opportunity to put these theories to the test in a very real, very concrete way. By analyzing jet substructure in even greater detail, we might be able to see subtle differences in the data that reveal which theory has the edge.
That is seriously cool. But we can't forget, the LHC itself is almost too good at what it does. You mentioned a pileup problem earlier. What's that all about?
Right, so the LHC is so phenomenal at smashing protons together that sometimes we get multiple collisions happening at practically the same time. Imagine a multi-car pileup, but on a subatomic scale.
Yikes. That doesn't sound very scientific. More like something out of an action movie.
You're not wrong. It makes analyzing the data incredibly challenging because now you have all these extra particles flying around from these unwanted collisions. It's like trying to have a conversation in the middle of a rock concert.
Good luck hearing anything over all that noise. So how do physicists deal with that?
They get creative. They've developed some amazingly clever algorithms to help sift through the data and filter out the noise from these pileup events.
Algorithm to the rescue. Give me the highlights. What are these algorithms doing?
One technique, called jet area subtraction, is like noise-canceling headphones for particle physics. It calculates the average density of particles from these pileup collisions and then subtracts it, leaving you with a clearer picture of the jet you're trying to study.
So it's like removing the background static so you can actually hear the music. Pretty smart. What about those other techniques you mentioned, like jet grooming? Do those help with pileup too?
They do. It turns out those jet grooming techniques, trimming, filtering, and pruning away extraneous particles from a jet, also help mitigate the effects of pileup. By cleaning up the data, getting rid of low-energy particles that are probably from pileup events, it becomes easier to isolate the real signal from that boosted object.
A 1-2 punch. First, they subtract the average pileup contribution. Then they use jet grooming to fine-tune the data and really zero in on that signal. That's some serious detective work.
It is, and the research you shared shows how absolutely essential these techniques are for making sense of the data, especially as the LHC ramps up its luminosity in future runs. That means even more collisions, even more data, and an even greater need for these sophisticated analysis tools.
Speaking of impressive particles, we can't wrap up this deep dive without giving a shout-out to the heavyweight champion of the particle world, the top quark. What makes this particle so special?
Well, for starters, it's the heaviest fundamental particle we know of. It's about as massive as a gold atom, which is mind-blowing when you think about how incredibly tiny it is. Imagine a single atom weighing as much as a small coin.
Talk about punching above its weight class.
Yeah.
So it's massive, but there's more to it than that, right? Why else are physicists so obsessed with the top quark?
Its large mass makes it incredibly sensitive to new physics. Many theories that go beyond the standard model, our current best understanding of particle physics, predict that the top quark might interact with new particles or forces that we haven't discovered yet.
So if the top quark starts acting even a little bit strange, it could blow the standard model wide open.
Exactly. And that's why finding and studying these boosted top quarks is so important. The higher their energy, the better our chances of observing tiny deviations from the standard model, little hints of something truly revolutionary.
Okay, so how do they find these elusive boosted top quarks in the middle of all the chaos of an LHC collision?
We talked about those general jet substructure techniques, but physicists have also developed specialized algorithms designed specifically for identifying top quarks.
Like a top quark fingerprint kit? Give me the details.
One of the most common is called the JHU tagger. It looks for a very specific three-pronged decay pattern within a jet, which is a telltale sign of a top quark. It's like recognizing a dog by its bark. Different particles have different decay signatures, and this one screams top quark.
And there are other tools in the toolbox as well, I imagine.
Absolutely. There's the HEP tagger, which is especially good at lower energies, and researchers are constantly developing new and improved algorithms. It's a very active field of research because these top tagging algorithms are key to unlocking the top quark secrets.
It's incredible how these algorithms are like precision instruments, helping us dissect and understand the subatomic world.
It really is. It's like having a super-powered microscope that allows us to see not just individual particles, but also the intricate dances they do, the stories they tell.
Beautifully said. It's clear that the study of boosted objects and jet substructure is pushing the very boundaries of particle physics, revealing the universe's tiniest constituents in unprecedented detail.
And this is just the beginning. The LHC is constantly being upgraded, and physicists are developing even more sophisticated techniques to analyze the data. The next big discovery might be right around the corner.
Now that's an exciting thought. And that wraps up our deep dive into the world of boosted objects and jet substructure. We've journeyed from the mind-boggling energy of the LHC to the elegant algorithms that help us make sense of it all. It's a true testament to human ingenuity and our insatiable curiosity about the universe.
We've seen how these techniques are not only deepening our understanding of the particles and forces we already know, but also opening up exciting new avenues to discover physics beyond the standard model. The future of particle physics is incredibly bright, and it's happening right now at the LHC.
What a journey. So until next time, keep those minds curious and never stop exploring the wonders of the universe.